This is Lecture 2 of Abstract Algebra, and this is on properties of operations. So in the last lecture, we defined an operation star on a set A to be a rule such that for any elements A and B in A, the ordered pair A comma B is assigned to exactly one element A star B in A. So many of the operations we commonly use have some additional properties. So for example, addition on the real numbers or on the integers, or multiplication on the real numbers or the integers, and so on. Many of these have some of the following properties. The property of being commutative or commutativity, the property of being associative, having an identity element, and having inverses. So just a note, these are not properties that an operation must have. They are just some bonuses that some operations do have. So we're going to define each of these and give some examples and some non-examples. So our first example is commutativity. An operation star on a set A is commutative if for every pair of elements A and B in A star B is equal to B star A. So multiplication on the set of real numbers R is commutative. It's true that for any two real numbers, A times B is the same as B times A. Matrix multiplication is not commutative. So if you've had linear algebra, then that's an example of an operation that's not commutative on a set. As a easier example, subtraction on the set of real numbers is also not commutative. So 2 minus 7 is negative 5, 7 minus 2 is positive 5. Those two elements are not equal. A minus B in general is not equal to B minus A. Our next property we'll talk about is associativity. So an operation star on a set A is associative if for any set of three elements, A, B, and C in the set A star B star C is equal to A star B star C. So in other words, the order in which we associate them, if we have parentheses around B star C, that means we're performing that operation first, and then we're also operating by A on the left. So I'd like you to think for a moment about each of the following. Is multiplication associative on R, the set of real numbers? And is division associative on R minus 0? So just as a reminder, in the last video, we saw that division is not an operation on just the set of all real numbers because, like, for example, 2 divided by 0 is undefined, but division is an operation on the set of all real numbers except for 0. So that's what that R minus 0 means. That's all non-zero real numbers, positive and negative. Okay, so I'd like you to think about each of those for a moment. All right, so is multiplication associative on R? Yes, in general, it's the case. It's always true that A times B times C is the same as A times B times C. It's just equal to A times B times C for all numbers, for all real numbers A, B, and C. What about division? This is not associative. So if you want to show that something does not have one of these properties, you want to show a specific example. If you want to show that an operation on a set does have one of these properties, you need to make a general statement or proof, depending on the situation. So here, is division associative on the non-zero real numbers? No. As an example with nice numbers that come out well, for example, 16 divided by 4, then divided by 2, that's 4 divided by 2, which is 2. Whereas if we associate the other pair, 16 divided by 4 divided by 2, that's 16 divided by 2, which gives us 8. So division is not associative on the non-zero real numbers. Our next property is having an identity element. So we say that the operation star on a set A has an identity element if there's some element E in the set A, such that for all elements A in A star E is equal to E star A, which is equal to A. So E operated with any element gives that element back. So let's look at a couple examples. So does addition have an identity element on the set of integers Z? And if so, what is it? Does multiplication have an identity element on the set Z, the set of integers? If so, what is it? Now let's define an operation A square B. Let's say that A square B is the maximum of the two elements A and B. So does this have an identity element on the set of integers? And if so, what is it? And finally, same operation, A square B is the maximum of the two elements A and B. Does that have an identity element if we're operating on the set of natural numbers N? And just as a reminder, Z, the set of integers, is the set of all positive and negative whole numbers as well as 0, whereas N, the set of natural numbers, is the set of positive integers, the counting numbers 1, 2, 3, 4, etc. So pause a minute. If you don't have paper out, I'd highly recommend grabbing some paper and just thinking about each of these briefly. Do these operations on these sets have identity elements? Okay, so first two, does addition have an identity element on the set of integers? Yes, 0 is the identity element, so 0 plus A is equal to A plus 0 is equal to A for every integer A. Does multiplication have an identity element? Yes, 1 is the identity element, so 1 times A is the same as 1 times A times 1, which is just A for every integer A. So each of those has an identity element. Let's think about the other two. So A square B was equal to the maximum of the two elements A and B. So if we had, -4 and -302, then -4 square, -302 would give us -4, the maximum of those two elements. Is there an identity? No, there is no one integer E such that A square E is equal to equaling the maximum of A and E always gives A as an output. So there is no E such that that's true. If we said, okay, let's let E be a really, really big, large negative number, let's let E be like -1,000,000, then yeah, that gives A back for most values of A, or not for most, but for everything larger than -1,000,000. But if we put in A equals -1,000,001, then we don't get A back. So this does not have an identity on the set of integers Z. What about on the set of natural numbers? Well, there is a minimum natural number. That's the element 1. 1 is the smallest natural number. So for any natural number A, if we take A square 1, that's the maximum of those two elements. A is always going to be at least as large as 1 if A is a natural number. And so therefore, yes, A square 1 is always going to be A, and 1 square A is always going to be A for any natural number A. So therefore, yes, square, this operation, does have an identity element on N, the set of natural numbers, but not on Z, the set of integers. All right, and our last property we'll talk about here is inverses. So in a note here that's important, in order for inverses to be defined at all for an operation on a set, there must be an identity element. If the operation does not have an identity element, then inverses cannot exist. So let's define now. Let's suppose that star is an operation on a set A, and E is the identity element. Let A and X be elements of A. Then A is the inverse of X if A star X is equal to E and X star A is equal to E. So if A operated with X in either order gives the identity element back, then a and x are inverses of one another. So we say that an operation star, just in general, sort of has inverses, has the inverse property, if every element of A has an inverse. That is, E is the identity element, and for any A in A, there is some X in A such that A star X is equal to E and X star A is equal to E. So let's look at a couple examples here. So here are our two examples. We'll look at Z, the set of integers with addition, and we'll ask, is it the case that every element has an inverse? If so, let's describe the inverse of a general element, A and Z. And if not, let's give an example of an element that does not have an inverse. Similarly, same question for the set of integers with multiplication. Does every element have an inverse in this set with this operation? If so, describe this inverse of a general element, and if not, give an example of an element that does not have an inverse. So give each of these a try. Again, grab your piece of paper, just think about these for a moment, and then we'll talk about them. Okay, in the integers with addition, does every element have an inverse? Yes. So for any integer A, negative A is its inverse. A plus negative A is equal to 0. So for example, if A was equal to 2, then negative 2 would be its inverse. If A was equal to negative 11, then negative 11, which is positive 11, would be its inverse. So yes, every integer has an inverse under the operation plus or addition. What about with multiplication? So if we look at the integers with multiplication, does every element have an inverse? Here our answer is no. So for example, 2 is an integer. We know that 1 is the multiplicative identity, but there is no integer x such that 2 times x is equal to 1. The value for x that makes that equation true is x equals 1/2. 1/2 is not an integer, and the x, like both the a and the x, the element and its inverse, must both be an a. So Z with multiplication does not have the property of inverses.